All right, so we looked at energy, just introduction there earlier on today. And today what we're going to do is, for the rest of the day, is we're going to look at different types of energy and how they relate to work. And essentially, well, we'll talk about that in a second here, the work-energy theorem. But our first specific type of energy that we're going to look at is kinetic energy. And kinetic energy is the energy an object has because of its motion. All right, and so the formula for kinetic energy, which is going to be EK, energy with a little k. And again, the kinetic, that's a Greek word that means motion. So that's where that comes from. And how we find kinetic energy is its mass. And because it's dealing with motion, times velocity, but squared and divided by 2. All right, so again, let's throw that down here. M is the mass. Is the mass, and v is, well, your velocity, your speed, I guess. Same thing in this case, because we don't need direction. We're just talking about energy, and energy doesn't necessarily have a direction, so speed and velocity. Now, again, how this relates to work is that, the work, and this is something I talked about earlier, didn't really define it. The work applied to a situation is equal to the change, and that's something we talk about, in energy in that situation. All right, and so for example, or what we could look at, I guess, in terms of a formula is that if you have work, that is going to be equal to your change in energy, whether it's kinetic energy or any type of energy, really. So that's delta E. Again, delta means change, so this is referring to a change in energy. So if you change something's energy, you speed it up, you've done some work in this case. And there's other types of energy that out there that, again, we're going to look at another type later on today or in our next class. But if you do work, you change the energy in something. All right, and again, they're both measured in joules. All right, so let's check something out here. Example 1. A whale with a mass of 1,500 kilograms is swimming with a speed of 6 meters per second. Find the kinetic energy of the whale. All right, so again, I like to write down my variables here. So we have our mass, which is the 1,500 kilograms, like 3,500 pounds. And whales are huge. The velocity of this whale is 6 meters per second. All right, and we want the EK, as it's called, kinetic energy. All right, so again, I'm going to use my formula there that we just started with, where we have our EK is equal to our mass times velocity squared divided by 2. All right, now, going to have to follow some math rules here because we got that exponent there, so it's going to cause some issues. All right, so when I substitute in here, my mass, again, is 1,500 kilograms of this whale. We have a velocity of 6, so I'm going to have a 6 squared. All right, and then a divide by 2. Now, as I mentioned, math-wise, got to follow our math rules here, so I got to follow bedness. Now, I got brackets, but nothing's going on in the brackets. But the next thing up here is my exponent. So I got to do this 6 squared before I do anything. All right, so I'm still going to have this 1,500 here. All right, and now I take 6 and I square it. So that's 6 times 6. I know that's 36. And then I divide by 2. All right, so we've got to do that first. Now my kinetic energy, the next step, I can do it all at once here because I can take 1,500, or 1,500, times it by 36 and then divide by 2. That can all be done at once. And I end up with 27,000, and we're talking about energy here, joules of energy. Again, we have a big object here, so more, again, your kinetic energy is based on how big and how fast you're going. All right, so in this case, the whale is both big and I guess he's going okay speed for a whale. Now, let's check this out. A large ship passes the whale, and its wake increases the whale speed to 12.5 meters per second. Find the whale's new kinetic energy. See, we got a question here. Go ahead. Somebody raise their hand up.
Oh, it was me.
Yeah, go ahead.
So we have a third lesson at 11 o'clock, right?
Yeah, I'm just talking about I'll answer those questions after. If you got something about this example, I'm all for it.
Okay, never mind.
Yeah, I'll answer all that after. All right, so again, now this whale sped up, and so now I'm going to find the new kinetic energy of the whale. All right, so again, my EK is equal to, again, mv squared divided by 2. So the mass of the whale doesn't change. All right, so it doesn't change, but the speed does. Now we got a 12.5 in here, squared, and divide by 2. And as I said before, I have to do the exponent first. Math rules, right? Bedmas. And so 12.5 squared, that's going to be a weird decimal number for sure, I think. But I'm going to put my 1500 in here. Let's see. I got my 12.5 squared. And yeah, I do get a decimal. I get 156.25. All right. And I'm going to divide by 2. And just as I did before, I can do this all in one step. I just take my 1,500, times it by 156.25, and then divide by 2. And yeah, I end up bigger. Again, it's going to be a bigger number because the whale is going faster, and I get 117,187.5. And again, we're talking about energy, which is joules. All right, so again, the whale increases its speed, it increases its kinetic energy. And then we get to see here, calculate the work done by the water on the whale. So it was going 6 meters per second. Now the whale's going 12.5 meters per second, and our energy changed. And so again, with work that's gone into it, we're looking at our change in energy. Again, that hashtag's for delta, change in energy. And so we ended up with, or the whale ended up with 117,187.5 joules of energy. That's what it finished with. It started with, what was it? I believe it was 27,000 joules of energy. And so if I subtract those two numbers, that's going to tell me how much the energy's been increased. In other words, how much work has been done on the whale. And when I subtract those numbers, I get 90,187.5 joules of work. That's quite a bit of energy that has been done on the whale to speed it up. All right, let's see here.
Wait, never mind.
Yep. Okay. What do we got here? Example 2, police car, 2,400 kilograms. That's probably a little big for a police car. Might be a tactical vehicle. At rest, receives an emergency call, and so the driver starts in motion. Okay. The increase in speed from rest results in 300,000 joules of work done on the car. Determine the police car's speed. All right. So again, writing down the information here. I got the mass. Be a little bit tougher here. 2,400 kilograms. The amount of work done on the car, which went into increasing its kinetic energy, because it was at rest, which means it had no kinetic energy, but now it has 300,000 joules added, and we want to know how fast that car's going now. All right, so again, I'm going to use my formula here, which is our EK, kinetic energy is equal to mass times velocity squared. And I can never forget my divide by 2 here. All right, so I'm going to substitute in here. So what do we got here? We got 300,000 joules of energy. All right, my mass is 2,400. So I'll put that in there as best I can anyways. There we go. I got my V squared here. And of course, my divide by 2. Now, I can simplify this. There's a lot of different ways to simplify this, but I think the easiest way is I can just take this 22,400 and divide it by 2. And so, This 300,000, that ain't going to change over on this side. All right, but if I take 2,400 and I cut it in half, divide by 2, if you will, I'm going to get 1,200. And again, I got that V squared. All right, so again, the whole point here is I got to get this V by itself. So I got to get rid of this 1,200 and this little 2. Well, I can do the 1,200 right away. So I'm going to divide both sides by 1,200. All right, so those 1,200s divide each other out. So then I got, let's see here, 300,000 divided by 1,200. Whoa. Oh, okay. I just get 250. And that is now going to equal our V squared. How am I going to get rid of that little 2, though? I'm not going to divide by 2. Anybody know how I'm going to get rid of that little 2?
Square root.
You got our square root. So I'm going to square root both sides here. All right, and my V is going to be my velocity or my speed, whatever you want to call it. And the speed of this car, I take the square root of 250. I get 15.81. And again, because we're in our standard units, that is talking about meters per second. It's actually not that fast, to be honest with you. It's probably because my weight, my mass here that's too big to be a car. Should probably have been half that, but anyways, I just made the example up. All right. So again, there's a little bit tougher to find the V because it's a V squared there, right? So it's a little bit tougher. What else we got here? An archer pulls back her bowstring loaded with a 22-gram arrow and then releases the string. If the arrow leaves the bowstring at 80 meters per second, calculate the work done on the bowstring. All right, so let's get to a few things first. Is that we're going to find the work done on the bowstring, and work is going into changing the kinetic energy of this bowstring. And of course, your arrow is not moving initially. So all that work is going into, creating kinetic energy. All right, now we have a bit of an issue here with mass. Our mass here is 22 grams. Anybody know how many grams are in a kilogram? We've done centimeters, meters quite a bit, but how about grams? 1,000. You got her, 1,000. So I got to take this 22 here and divide by 1,000, and I'm going to get 0.022 kilograms. So we got to be in our standard units here, right? We do know the velocity of this bow. It's or this arrow, I should say, 80 meters per second. All right. So to find that work done in it, let's see here. Nope, nobody raised their hand or anything. Okay. So our work that's done on the bowstring, which again is going into kinetic energy, it's going to be our mv squared divided by 2. Always got to throw this in.
Oh,
here.
I raised my hand, by the way.
Okay, go ahead. What do you got?
I just want to know, how do you know that you need it to be kilograms in this question?
Because every time that we're dealing in physics, we have to have everything in its standard units. So your mass always has to be in kilograms. Your velocity is always in meters per second. Your distance is always in meters. Time's always in seconds. You got to have everything in its standard units. Yeah, good question. All right. So now that I have made that happen, put my work in here. My mass, very small, right? So again, maybe not a whole lot of kinetic energy because it's so small, but yet the thing's moving fast. So we'll see here. My velocity is 80. I'm going to have an 80 squared. All right, divided by 2. All right, so as I've said before, got to follow Bedmas here. So I got to do that 80 squared first here. So I got my 0.022. All right, 80 squared. 6,400, 6,400. All right, there it is. And of course, can't forget the divide by 2. I don't know how many times people forget the divide by 2. All right, so the work, which is in joules, how much energy is put into this arrow, which is turned into kinetic energy. I take my 0.022, I times it by 6,400, and then divide by 2, and I get, again, going to 2 decimal places, I get a 70.1 0.4. And again, we're talking about joules. All right. So again, even though the speed was really fast, the object isn't that big. So again, the kinetic energy is not that much comparatively. All right. Now, what is the magnitude of the force the bowstring exerts on the arrow? Over 10 centimeters. So again, we are looking for the force. This is going to tie into what we did earlier today. All right, we're looking for the force. Now, we know how much work was put in here. It was 70.4 joules of energy. And tying into your question we just had, we got 10 centimeters as our distance. Well, that's not in standard units, so I got to make a conversion again. And this is one we've had before, converting centimeters to meters. Again, there's 100 centimeters in a meter, so if I divide by 100, I get 0.1 in this case, meters. All right. So this we know the amount of work, we know the distance, and we're looking for the force. Well, this is tying in with our formula we had earlier today. Work equals F times D. All right, I know the work is 70.4. We're trying to find that force, and our distance here is 0.1. All right, well, all I need now to do is to get F by itself, I'm going to divide by my 0.1. What I do to one side, got to do the other here. All right, so those 0.1s cancel each other out or divide each other out. And so our force here is 70.4 divided by 0.1. And I end up with, round number here, 704. And because, again, we're talking about a force, it's 704 newtons. It's how much force that bowstring exerted on the arrow to make it go 80 meters per second. And it only took 10 centimeters to do that. So that's quite a short amount of time. All right. So again, that's how work and energy are related.